Let's take a look at working with normally distributed data and using the empirical rule. The learning objectives for this video are to first do a quick review of the terms associated with working with population data, sigma, mu. We'll also take a look at process data and spend a little bit of time discussing why it's frequently normally distributed and what we can do if it's not. But most of the time will be spent taking a look at normally distributed data and the empirical rule, sometimes called the 68, 95, 99.7 rule. And we'll visually explain what the concept means. All right, in this example, I've gone out and I've collected some process data. Could be current state, could be future state. One of the first things that we'll do with this process data is we'll ask the question, is it population or sample data? If it's population data, some of the things that I'm looking for is it a very large data set? Does it contain all of the occurrences? Is it something that reflects a long span of time where the process hasn't changed over that long span of time? If it is population data, I'm going to be looking for information about what is the central tendency of this data set and what's the amount of variation. Earlier videos have shown why it's so important to collect both of those descriptive statistics when you're analyzing process performance. When we're working with population data and we're trying to understand central tendency, typically we'll be taking a look at the mean. For variation, we'll be looking at standard deviation. And there, the mean is represented by the symbol mu. And for standard deviation, the symbol is sigma. If instead we were looking at sample data is going to be a smaller data set. It could be over a smaller period of time, or it could be a subset of the data from the big pot of data known as the population. The mean is represented by the variable x bar. Sometimes written out as x bar, other times written as an x with a bar above it. Sometimes, because that's hard to do in a word processor, we'll put x bar with a bar behind it or below it. When we're looking at standard deviation, the symbol that we use for standard deviation is S for samples, sigma for populations, S for samples. For central tendency, mu for mean. For samples, it's x bar. In addition to calculating some of the descriptive statistics for central tendency and variation, we'll frequently want to get a visual display of that data set. I like to use histograms. Number of reasons why I like histograms. Histograms allow us to see central tendency. They allow us to see the amount of variation. They also allow us to see if there are any outliers or if there are any other unusual factors, especially around constraints that we might have to consider. If the data that we are capturing has many underlying variables that affect the performance output, say these are wait times, or this is length of a piece of lumber that's being cut off of a particular saw, or it's temperature settings or height settings. When you've got many underlying variables that affect that performance data, and there are no nearby constraints that are limiting what the output values could be from a low to a high value, the central limit theorem says that the data when plotted as a histogram should look like a bell-shaped curve. One of the reasons why I like histograms is if I plot it out and the data is supposed to look like a bell-shaped curve and it doesn't, that gives me some great insight as a process performance analyst. I can start to ask questions about, well, if it is supposed to look like a bell-shaped curve and it doesn't, why is that the case? Some common examples of when I would expect data to look like a bell-shaped curve and it doesn't, the output histogram might look like this. In that example, what I've got is data that's skewed in one direction and an abrupt stop that occurs. For example, it could be time-based data where you can't go below 0 for a time value. Another example of histograms where I would expect it to look like a bell-shaped curve, but it might not, could be a visual that looks like this. A chopped off bell-shaped curve where no additional values are allowed outside a particular point and no lower values are allowed. This could be an indication that the tools we're used for measuring are restricting the information. It could be a physical constraint that limits it from going high to low. But honestly, the most frequent example of a display where it should look like a bell-shaped curve and it doesn't is something like this. In this example, what I've got is a double humped curve, which is typically an indication that you have lurking subcategory types. You might have this is what one branch's output looks like, and it's combined with another branch's output. This could be the male group versus the female group. This could be shift 1 versus shift 2. But when all of that data is combined together, it looks like a multi-humped histogram. So visually displaying the data as a histogram gives us great insight. We're going to assume, though, for this next piece that the data has been plotted out. We've captured the descriptive statistics. We understand what the mean and standard deviation is. And when we plotted out the data as a histogram, it looks like your standard normal bell-shaped curve. When that is the situation, some very simple and interesting tools can be used. We call it the empirical rule. The empirical rule is used when you're working with population data sets. All right, in this example, I've got my data plotted out as a histogram, and when plotted out, it looks like a bell-shaped curve. We know from earlier discussions that for normally distributed data, right down the middle, that'll be where our mean is. We're going to call that mu. We also know from earlier discussions and earlier videos that we can visually identify where standard deviation is. It's where the upside down bowl meets the sideways bowl of your bell-shaped curve at this point here, and by measuring that distance to the middle, that is your standard deviation. So now what I'm going to do is I'm just going to drop down that standard deviation on both sides. We'll call this plus 1 sigma minus 1 sigma. And what the empirical rule tells us is that for all normally distributed data, all bell-shaped curves, whether they're fat bell-shaped curves or skinny bell-shaped curves, the number of data points that fall inside your plus and minus 1 standard deviation is always the same. The number of data points that will fall within this plus or minus 1 standard deviation is always the same, and it's 68%. Now what I'm going to do is I'm going to take that same standard deviation distance and I'm going to extend it out. I'll go out to plus 2 standard deviations. And I'll do the same thing on the other side. What the empirical rule tells us when we go out 2 standard deviations for any bell-shaped curve data, which is what most business data, most process performance data is going to look like. It's going to, when plotted out, look like a bell-shaped curve. What the empirical rule says is when you measure out 2 standard deviations of distance from the mean, the number of data points is always the same. Whether you've got a fat bell-shaped curve or a skinny bell-shaped curve, it's always the same. The number of data points plus or minus 2 standard deviations is 95%. And now what I'm going to do is I'm going to go out 1 more standard deviation in distance. So we've gone out 1, 2, let me go out the same distance and go out 3 standard deviations. Do the same thing on the other side. And what the empirical rule says for normally distributed data is that the number of data points that are within plus or minus 3 standard deviations, it's always the same. That value, 99.7%. So within plus or minus 3 standard deviations, we are operating with 99.7% of the data. Another way to describe that is to say that there's only 3 out of 1,000 data points that fall outside of 3 standard deviations. So if we look at that red region that is outside of 3 standard deviations, 3 out of 1,000 will fall in those combined areas. We call this the empirical rule. Keep in mind this powerful rule only applies for normally distributed data. When we have normally distributed data, we can say within plus or minus 1 standard deviation, 68% of our data points will fall. If we are within 2 standard deviations, it's 95% of our data points, and within 3 standard deviations, it's 99.7%. Only 3 out of 1,000 data points are going to fall outside of 3 standard deviations if you're dealing with normally distributed data. The empirical rule gives us a lot of great insight into process performance data. When we've captured a data set, it's very straightforward to calculate standard deviation, that distance. Once we have that distance, we can start to see immediately and start to calculate what the percent of data points are that are within any one of these regions on the bell-shaped curve. If we add to it what our performance specification limits are or what our customer needs are, we can get a pretty good understanding of how well process performance is meeting those needs. The empirical rule is a great kind of back of the envelope, simple way to get some understanding of how good or bad is the performance data that you're looking at. In the next videos, we'll take a look at some specific problems, applied problems, and use the empirical rule to gain some insight on them.